Yeah, hi everyone. I'm very excited to be here today to talk about Lifejacket, a tool for verifying precise floating point optimizations in LLVM. This is joint work with Fraser Brown, and as kind of the title of the talk suggests, we are interested in automatically verifying floating point optimizations. And so to kind of motivate why we would want to do this, let's take a look at an example. So let's say we have this very simple floating point expression that we would like to simplify. Now, one way that you could come up with is to say, well, this is essentially just doing minus minus x, which is the same thing as just saying y is equal to x. Unfortunately, floating point arithmetic has the notion of negative and positive zero, and so in the case of the unoptimized code, if x is minus 0.0, then you get y equal to positive 0, whereas in the optimized case, it stays negative 0. Now, okay, we've seen that for certain values, there might be a difference with this optimization in terms of results. But you might say, well, positive 0, negative 0, there isn't a huge difference between the two. And in fact, if you compare them, you would get true. However, there can be a problem if you continue to use the value or the result of this expression later on. If you, for example, compute 1 over the y that we had before, you would get infinity in one case and negative infinity in the other. And if you compare infinity to negative infinity, then you actually get false. And also the difference between the two values is fairly large. So, yeah. In addition to all this positive, negative 0, and infinity values, floating point arithmetic also has the notion of not a number values, and those values are kind of, those values stand for things that can't be expressed reasonably as a number. So for example, if you add infinity and negative infinity, then you get not a number. And those special values have, in turn, their own rules. So if you, for example, add not a number to another value, you again get not a number. But not only do you have to deal with those special values, you also don't, like the rules for arithmetic don't really hold in the case of floating points. So you don't get associativity, and you also don't get distributivity. And as you can imagine, if you would like to implement new optimizations or kind of reason about existing optimizations that deal with floating point arithmetic, this is very hard to do manually because you have to think about all the edge cases, and yeah, it's just time-consuming and complicated. And so we would like to automate this process, and this is what Lifejacket is about. So we're, of course, not the first ones that are kind of interested in automatically verifying optimizations. And in fact, Lifejacket is built on top of an existing system called Alive, which is a system for verifying peephole optimizations in LLVM, created by Nuno Lopez et al. And it roughly works as follows. The user specifies an LLVM optimization in a domain-specific language. Alive then translates this specification into a series of SMT queries, and I'm going to talk about SMT solvers in just a little bit. And then Alive uses an SMT solver called Z3 to either verify that an optimization is correct or find a counterexample that says why the optimization is incorrect. And while Alive is great, it unfortunately didn't support floating point arithmetic, and this is kind of where the idea came from to extend it with support for floating point arithmetic. Now, just kind of as a full disclaimer, I should mention that some of the original authors of Alive, simultaneously, they also extended Alive with support for floating point arithmetic, and yeah. So just kind of as a side note about SMT solvers. So SMT solvers are solvers that take as an input a first-order logic formula extended with some additional functions and predicates. So you get a rich language. You can, for example, ask the solver x is smaller than y and y is smaller than x minus 1, and the solver will tell you whether there is any assignment for the variables such that this formula is true, or it will tell you that no such assignment exists. And this is a very powerful tool for program verification and can also be used for optimization verification, because it essentially checks for all possible cases. And yeah, so you can leverage that to check the optimizations. Now let's take a look at what the optimization from before would look like in Lifejacket. So we have the informal description up here, and that roughly translates to the following. So you have the source pattern up here and the target pattern down here. That's the right-hand side. And so this, the negative x here corresponds to the first instruction, and the subtraction corresponds to the second line here. And this is, it's very similar to LLVM syntax. The main difference being that you don't have to annotate the floating point types explicitly. Actually, Lifejacket is able to automatically figure out which types the optimization might apply to. And that's kind of similar to what the Life did for integer types. Now, if we feed this optimization into Lifejacket, it translates it into a series of SMT queries, and it comes back with a counterexample that we saw previously. Now, I should note that for the purpose of this talk, we're really interested in floating point optimizations that are precise, that preserve the kind of bitwise meaning of the program. Now, for the remainder of the talk, I would like to talk about the floating point types and the instructions that Lifejacket supports, as well as the fast math flags. So we support the typical kind of half, single, and double precision floats, and as well as the standard binary instructions like addition, subtraction, and so on, conversions from floating point types to integers, and then also computing the absolute value and comparing floating point values. For most of these basic instructions, there is actually quite a straightforward translation because the SMT standard defines similar operations. For some operators like FREM, the translation is a little bit more complicated, but in general, it's relatively straightforward. Where things get a little more interesting is with fast math flags. As some of you may know, in LLVM on floating point instructions, you can have fast math flags, and those basically tell the compiler that it can apply some additional optimizations, or that it can take some additional assumptions. So Lifejacket currently supports 3 types of fast math flags. The first one is not a number, and what this fast math flag says is that this instruction does not expect not a number either as an argument or as a result. And if it happens to get not a number as an argument or a result, the result is undefined. And similarly, not infinity says that we don't expect positive or negative infinity for the arguments or the result of the instruction. Finally, the last fast math flag says that we don't care about the sign of 0 values. So with this flag, actually, the first optimization would have been correct. Now let's take a look at an example of an LLVM optimization that actually exists that uses fast math flags. So up here we have again the informal definition of the optimization. And so if we translate that to the Lifejacket input, it would look something like that. So we're being here kind of conservative, and we're saying that we don't really care if there are not a number values or infinity values. Then we say we can have kind of any value here, and it should be fine. Now, the way we translate this into an SMT query is that we basically add some additional restrictions, and we say that if any of the arguments or the result happens to be not a number or infinity, then the result here is unconstrained. Now, we can ask ourselves whether this optimization is correct. And even though we have those additional fastmath flags, it turns out that the optimization is not correct. And the reason for it is that x could be not a number. And in this case, so we get, if x is not a number, we get an unconstrained value here, but that doesn't really save you, because if you add not a number to any value, then you again get not a number, and not a number is different from 0. So this optimization is actually not correct. Now, I would like to give you an overview of the results that we found. So we were able to verify 43 optimizations in LLVM 3.7.1. We got 3 timeouts on the optimizations that we tried to verify, and we found 8 optimizations that were incorrect. Kind of our insights from this experiment was that we got surprisingly few timeouts, considering that floating point arithmetic is very difficult to deal with for an SMT solver. We were also surprised by how many optimizations that we found that were incorrect. And it was interesting to see that all the kind of incorrectness came from some special properties of floating point arithmetic. While Lifejacket works fairly well, it currently has some limitations. We don't support types wider than 64-bit, and this is not a fundamental limitation. It's just that we started with kind of the most common types. We also use a fixed rounding mode for now, and we do not support floating point exceptions and debug information in not a number values. Now, for the last 2 points, to the best of my knowledge, LLVM doesn't really support those cases either, so that's why we didn't really spend time on that. What's kind of nice, however, is that if Lifejacket finds an error, then you can actually be sure that this is an error, because it also gives you a counterexample. Yeah, so in conclusion, I think we showed that verification of floating point optimizations is possible, at least in certain cases. And I would also think that it is necessary to do so in order to create compilers that are more boring and to enable kind of creating new optimizations that you can verify and be sure that they are correct. Thank you.
Okay, so you're an entire minute under your time, which means we have lots of time for questions.
Hi, I have a question regarding the SMT solver. So actually it's 2 questions. First, you mentioned that the SMT solver has some trouble dealing with floating point. But you didn't mention which theory you use to encode the floating point numbers into the SMT. The second point was you mentioned there were 3 timeouts, but which timeout did you actually use? So
Oh,
like 24 hours or 48 hours?
No, so the timeout was fairly short. It was 30 minutes per query. So yeah, it was fairly short. We used the theory of floating point arithmetic, and yeah. Sorry? Bit vectors? We did not try bit vectors, no. Okay. Yeah.
So, the most important question of all, did you submit patches to remove the broken optimizations you found?
I submitted bug requests.
Were they fixed? Okay, I'll follow up with you later to see which ones those were.
Okay, yeah. Down here.
Thanks for the talk. One thing I just want to point out is that the LLVM language doesn't actually specify that you have to use IEEE 754. So in some cases, like the optimizations that you are saying along actually might be right on the platform where IEEE 754 isn't used. But I think most platforms do use it, so it probably doesn't matter.
Yeah, it's somewhat underspecified, I guess. Yeah, in that sense.
Well, the LLVM is underspecified here. I believe the strong intent of everyone working